All right, so past climates. Determining a history of Earth's past temperature is challenging. Scientists infer it from proxy data, which are other data sets that are a function of temperature. The most useful recent data set starts with the evolution of hard-shelled life forms at the start of the Cambrian period, about 540 million years ago. This record shows periods of ice ages when significant amounts of water were stored on land as glacial ice sheets, and warm periods when there was little ice. Glacial periods have lasted for tens of millions of years. Earth has been in one such cold period for the past 50 million years. Not much is known about ancient climates for the first three-fourths of Earth's history because so few rocks remain from this time. Okay, so oxygen isotope data. Past temperatures can be inferred from the ratios of O16 and O18 isotopes in clamshells. Because O16 is lighter than O18, the O16 isotopes evaporate more easily. Rain, snow, and glaciers therefore contain very little O18, which stays in the ocean. Time periods that show an increase in O18 in clamshells indicate that a great deal of ice containing O16 was stored on land in glaciers. So over here we've got the fan or Ozoic climate change, okay, and the y-axis shows oxygen 18 parts per thousand, and then the x-axis shows millions of years ago, okay. The blue solid line shows the short-term average. The red dotted line shows the long-term average. And then the light blue shows the glacial period, okay? So we want to go ahead and calculate the mean time between the starts of cold glacial periods over the past 500 million years. So the mean is the sum of all the observations over the total number of observations. Okay, so we're going to be primarily focusing on these light blue glacial periods. Okay, so we're going to be estimating 470 is like right here. Okay, and then 340 is like right about here. So we're going to take 470 minus 340, and that equals 130 millions of years. Okay. Then we're going to take 340. We're going to estimate from 340 to 180. We see, and we're going to take 340 and subtract 180, which equals 160 millions of years. And then again, we're going to estimate, this is about 180 right here, and this is about 55. So we're going to take 180 minus 55 and get 125 millions of years. All right, so the changing composition of Earth's atmosphere. Earth's surface was blistering hot in its early years. It was almost completely molten, and greenhouse gases such as methane, water vapor, and carbon dioxide dominated the atmosphere. Life and the ocean gradually removed most of Earth's atmospheric CO2. So we've got the composition of Earth's atmosphere. On the y-axis, we have the percent of atmosphere. On the x-axis, we have time, billions of years ago. And some of the greenhouse gases that we see water vapor represented in purple, We see ammonia, methane, hydrogen, and helium, or ammonia and methane are represented in red, hydrogen and helium are represented in orange. Carbon dioxide is in green, nitrogen is yellow, hydrogen sulfide is dark purple, and then we have oxygen in light blue. So life and carbon dioxide. Life and carbon dioxide. Life has had a dramatic effect on all of Earth's surface systems, especially the atmosphere. If not for plant life and the ocean, the atmosphere would be mostly carbon dioxide. The ocean began removing carbon dioxide from the atmosphere more than 4 billion years ago. The later expansion of photosynthetic plant life brought atmospheric CO2 levels nearly to 0.04%, keeping Earth's surface from becoming too hot and uninhabitable. The atmospheric carbon removed by life was stored away in the ground as rocks such as limestone and fossil fuels such as coal, oil, and natural gas. So explain why it would make sense that the amount of water vapor in Earth's atmosphere would decrease as Earth's surface cooled. Where did that water go? So since warmer air, we know that warmer air holds more moisture, which means the concentration of water vapor increases. Okay? And so when the air cools, its concentration of water vapor decreases. When the Earth's surface is cooled, water vapor decreases due to the oceans. So over here we're looking at atmospheric carbon dioxide and the diversity of life. The levels of atmospheric carbon dioxide have fluctuated over Earth's history, as have the number of genera, which are groups of similar species. Scientists do not have a good way to measure the volumes of past biomass, but the diversity of life can be used as a rough indicator of the degree to which life had expanded. So again, we're looking at carbon dioxide and diversity. On the y-axis, it shows carbon dioxide in parts per million by volume. And on the x-axis, it shows millions of years ago. Okay? So again, in purple, we see carbon dioxide. And then the blue represents biodiversity. Okay? So the main thing that you want to get out of this is that when there is more diversity, like there is right here, there is a drop in CO2. Okay? So as you can see over here, when carbon dioxide increases, when biodiversity increases, okay, again, it's biodiversity is increasing, and then we see over here, carbon dioxide is decreasing. So again, more diversity shows that there's a drop in CO2, okay? Over here, we can tell that there's a mass extinction, okay? And when there's a mass extinction, the CO2 levels rise, okay, until biodiversity is stabilized. So again, more diversity means there's a drop in CO2. When there's a mass extinction, like the way there is here, CO2 levels rise until biodiversity is stabilized. So CO2 and biodiversity. Over the past 542 million years, the amount of carbon dioxide in the atmosphere has decreased, while the diversity and number of living things has increased. Okay, so you're going to observe the correlation between the patterns of the two curves. Okay, land plants evolved about 470 million years ago and expanded across the continents, developing into forests. Explain the carbon dioxide curve during this time. So again, 300 million years ago, a mass extinction caused CO2 levels to rise until biodiversity stabilized. Okay, and again, we're looking at volcanic activity and CO2. So while not occurring now, there have been times in Earth's history, usually associated with the initial arrival of mantle plumes of hot rock at the surface, when vast amounts of lava have erupted for millions of years. This volcanic activity has triggered extended warm periods. So, extended periods of volcanic activity and large amounts of CO2 to the atmosphere. So, there's areas of large flood basalts. Basalt rock forms when cooling lava. Okay, so due to mid-ocean ridge volcanism, the ocean seafloor is mostly basalt. However, there are times when large volcanoes have erupted for millions of years, sometimes in the middle of plates. These regions are called flood basalts. So again, this right here is the lithosphere. We've got the head right here, the tail. This is the tail. This is the rising plume, the mantle, and then finally the core. Okay. Over here, we see the flood basalt, the hot spot, the rising plume, mantle, and then the core. Okay, so again, over here, step one, heat conducted into the mantle from Earth's core can cause a plume of hot mantle rock to rise a few centimeters per year toward the surface. Okay, and over here, step two, when the mantle plume nears the surface, it spreads out along the underside of the lithosphere. Heat from the plume melts part of the lithosphere above it, causing eruptions of magma that then cool to form flood basalts. So the decon traps, large flood basalts covering much of western India, formed around 66 million years ago. What effects did their formation likely have on Earth's atmosphere? Explain. So the large flood basalt formation affected Earth's atmosphere due to the release of large volumes of volcanic gases like sulfur dioxide. The decon traps caused climate change because the temperatures dropped due to acid rain and the change in the composition of the oceans. Decon traps may cause mass extinctions as well. So, erosion and carbon dioxide. The chemical weathering of rocks removes CO2 from the atmosphere, reducing the greenhouse effect. Carbon dioxide in the atmosphere reacts with water vapor to form carbonic acid H2CO3, which makes rainwater slightly acidic and accelerates the weathering of minerals. The carbon, often in the form of bicarbonate ions, HCO3 minus, enters the ocean. It becomes part of the shells of marine organisms, and when they die, is stored away under the seafloor as sedimentary limestone. Periods of increased erosion, such as when large mountain ranges are uplifted, can contribute to global cooling through the removal of CO2 from Earth's surface systems. So again, over here we have the erosion of the Himalayan plateau. The high erosion rates of the Himalayan plateau over the past 50 million years have removed significant amounts of CO2 from the atmosphere. India has been moving northward for more than 60 million years, colliding with Eurasia and pushing up the Himalayan plateau. Okay, so over here we see the movement of air in India. Okay, we see the Eurasian plate, the Himalayan plateau, the zone of orogenesis, mountain formation, northward motion by Indian plate. And so if the velocities of tectonic plates were to significantly decrease, how would it have, or would it have a cooling or warming effect on Earth's climate? Explain. So when tectonic plates move quickly, increased volcanic activity vents more carbon dioxide into the atmosphere, causing the Earth to warm. When the velocity of the tectonic plates significantly decrease, there is a cooling effect.